Are we playing the theme song? Yeah.
Customer analytics using data to drive decisions. Segment price and predictive fueling career ambitions. Who buys more and why and when? What brings customers back again? Data are machine learning. Happy customers, jobs worth earning. Customer analytics using data to drive decisions. Segment price and predictive fueling career ambitions.
Okay, so today's format is going to be just slightly different. It's not a large difference, but we're going to go through a couple of motivating stories for the value of understanding heterogeneity in customers and the strategies that understanding can enable. Then we'll go through some math on how we extend the multinomial logit model to account for customer heterogeneity and enable us to estimate that heterogeneity. After that, we're going to go through an extended discussion of how do we pick what model to estimate, because that is a judgment that the analyst makes, which has to balance multiple competing criteria. Has anybody here ever heard of cross-validation before? Could you show me your hands if you've heard of cross-validation? I got 3 hands. Anybody not heard of cross-validation? Okay, most of the room. Okay, it should be as famous as R-square, but it's not for some reason. I think that's due to some intellectual traditions, which have been changing recently, but haven't gotten fully represented in recent course materials. So after we finish that discussion, we'll take a short break. We'll step through our script after that. I want to make sure we go through the entire script today. It's really important for not only this week, but the next couple weeks. And then in the time that we have remaining, we'll talk about conjoint analysis, which is probably the single most popular quantitative marketing framework and relies on heterogeneous demand models. And it's a nice application of heterogeneous demand models to stated preference data, and it's really, really powerful. Okay. Quidel is a medical supply company. They started out making test kits, and I believe they're still headquartered in Del Mar, right up the road. The story I'm going to tell you is not recent, but it is great. So if you interview for a role there, the person you talk to may know about this, may not know about this. I learned this story through a colleague who was involved. One of Quidel's more successful product categories was home pregnancy tests. And in the US, what they were doing is they would manufacture the test, they would sell the test to a wholesaler. The wholesaler would put the tests in a box, put a name on the box, put an image on the box, transport the box to the retail chains that sold it, and take a margin, nice healthy margin. And Quidel decided to enter a couple of European markets for the first time and decided rather than letting a wholesaler take its margin, Quidel decided to act as a wholesaler, which meant for the first time it would be taking responsibility for the box that the test strips were sold in. So it hired my former colleague to understand the market for home pregnancy tests. My colleague did a bunch of marketing research exercises. They broadly pointed to similar conclusions. There were 2 segments in the market for home pregnancy tests. They were roughly the same size and they had very similar demographics. Does anybody know what the 2 segments in that market for home pregnancy tests were? That is exactly right. One segment they called hopefuls. And the other segment they called fearfuls. And you can understand how they have similar demographics between the two segments because it's very easy to imagine that a woman might be a fearful in one occasion and then might become a hopeful a short time later, even with the same partner. So you can understand how the two groups had very similar demographics to each other. So this is a time varying customer need state more than it is a between customer difference. And so what I want to do with you next is my favorite 10 minutes of the course. It's really what this entire course is all about. Given this single customer insight, what Kidell decided to do is to develop two products, one targeting hopefuls, the other targeting fearfuls, and we're going to walk through the marketing strategy for each of those two products. So, the single most important choice we have to make, what is the name of the product that we're going to put on the box? If we are selling home pregnancy tests to hopefuls, women who want a positive test result, what are we going to call our product?
Baby to come.
Baby to come. You know, we have to be a little careful. We can't promise the result. We don't. Yeah, so I like the spirit of that, but can we deliver on that promise? That's not something we control. We sell the test strip.
Like first step.
First step. Interest. First step. Can anybody do better than first step? Oh, promising the result. Remember, this is not an easy process for every couple. A lot of people have a lot of trouble.
So if we're going for the hopeful, you could just call it hope.
Hope. Yeah, nice. All right, now, what are we going to call our product targeting fearfuls? People who are afraid that they might be pregnant and need to find out.
Yes.
My expression.
Wait and see.
Safe measures.
Safe measures. Safety first. First. Clarity. You need to know. Here's how you find out.
More choices.
Oh my gosh. More choices. I don't know. It's a little risky. Okay, so here's what they actually called them. Conceive, targeting hopefuls. They named it after the act, not the result. And targeting fearfuls. Rapid view. So once you buy this product, you won't have to persist in this state of uncertainty, which you may be finding unpleasant right now. You'll find out quickly. And so it's sort of communicated in the name, but building on that, the positioning of conceive was trusted info about when it's time. And again, it's sort of communicated in the name, but rapid view was peace of mind quickly. All right, now if we're designing the box for conceive, what picture should we put on the box?
Baby.
Yep, that's what they did. And if we're designing rapid view, what would be the single worst picture we could possibly put on that box? We're not gonna put a baby. What do we put? What's that?
A clock.
Clock. A frolic. Uh, a frolicking woman.
A picture of a negative result on the box, like the test, the negative result.
Yeah, it's tricky, right? It's because we can't promise the result. That's where we have to.
So would
a
that be
little
like
careful.
but wouldn't that just be like showing like a function of what it does? Like, oh, that's what it could look like.
Yeah, what they did was abstract geometric shapes. Because if you think about it, does she want to be seen buying this product? Does she want to feel obtrusive walking from the shelf up to the register? It's probably not something she's proud to be buying. And she might even be scared off of buying it if she feels embarrassed. So we want to make it actually pretty nondescript. So that's what they decided to do. Okay, let's do rapid view. How many strips do you put in the box? 2. How did you know it was 2? What's the logic for 2?
You have to be sure.
Here's one fails.
Yeah.
I was like,
Yep. 1 to check, 1 to make sure. What about in conceive? How big is the box? How many strips do we put in there? I heard 1, 2, 4, 5. You're all wrong. Well, think about it. If you're buying pregnancy test strips, you probably pulled the goalies a little while ago, right? And nobody scored yet. So you might anticipate a process. So yeah, big box, expensive. And what aisle do we want conceived to be sold on in the drugstore? Family planning.
fertility. Baby clothes.
We want to be next to the diapers, the formula, wipes. That's where she wants to be. She's been shopping in there, checking it out. And what about rapid view? Where do you want to be in the store? Oh, check out. Not perception.
Oh yeah, that's a good question.
Now, both of these products were quite successful, and the brands were extended to additional related categories. So what other products, test strips in particular, could you put under the conceive brand name? Yeah. Is it me or is it him? What about for rapid view? What else could you sell under that brand?
Control.
Well, Plan B is owned by another by a pharmaceutical. Birth control, they were not making it, so they were in the test strip business.
That's
Well, that's what rapid view is. Okay, this last one, often you can make an argument either way. Now, conceive is a much bigger box. I'm going to ask you on a per strip basis, which product retailed at a higher price? Okay.
I'm gonna assume it's the whole floor,
Why?
because there's like more like strips, so like that's more expensive, and then like, I don't know, if you need something like right away, like the fearful segment, you probably want it to be cheaper because you just are in a panic. You just kind of want to get the cheapest one because you just want to get over it.
But I think those who are in a panic are willing to like spend more money to get the result fast.
So a very common argument for Rapid View being higher priced is the more inelastic demand, given that you want to find out as quickly as possible. And that's a reasonable argument, but it neglects the reason that Conceive cost about 15% more per strip, despite selling in a much larger box of strips. So it's like a opposite of a volume discount. And the reason for this, many of you will find out in the future. And so this is for the future husbands in the room. When it comes time to start a family, there is a very common phenomenon of price sensitivity going out the window for a while. This is the most important thing she has ever done in her life. And she does not want cost consciousness to be a driver of key decisions. And if you see any females around you nodding their head, take note. And then just be very careful in some of those discussions. So yeah, many of you will find out. Now, the reason I talk about this story is because I submit that without that key customer insight about heterogeneity and customer needs that we started from on the first row, hopefuls and fearfuls, nothing that followed would have been possible. So this, I hope, illustrates the reason that understanding customer heterogeneity is so critically important, because that understanding can drive extremely profitable choices that also offer great customer value.
Wouldn't the age also be a pretty big driver? Because I feel like if you're hopeful, you probably are more financially stable than someone who's fearful. That might even be kind of in part why you're hopeful versus fearful. So does the age range basically have an impact? Or are we assuming that they're inconsistent even across age range?
The demographics between the two groups tended to be pretty similar. I do share your intuition that the hopefuls are more likely to be partnered and therefore economically a bit more secure. It's probably not a large difference, probably a small difference. And that could contribute to the price difference as well. Okay, my next example illustrating the same point is not quite as detailed. Has anybody here ever heard of the company Transsion? They had nearly a 50% market share of the African smartphone market when this article first came out about 5 years ago. And I checked again this week, and the estimates still put them at around a 45 to 48% market share in the continent of Africa. And the company attributes that to two main things. One, a focus on low-cost manufacturing, which enables them to sell their phones at attractive price points. Two, a very simple customer insight that led them to change their defaults in their smartphones. And the customer insight it's very simple. So many people with darker skin, they find that smartphone cameras on default settings don't take great pictures of them. And in Africa, what the company reports is that many consumers, when they consider which phone to buy, what's the very first thing that they do? They've had this experience, they open up the camera app, they take a picture of themselves, they go to the photos and they look at the picture. And from that initial experience of the picture quality using default settings, they then form a quality perception of the phone overall. And so what did Transsion do as a result of that customer insight? They tuned their default camera settings to optimize the various choices to take great photos of people with darker skin. And that's how they ended up with nearly half of African smartphone sales. Not long after this article came out, Pixel released a TV ad showing that if you change some of the settings in the camera, you can get great photos, including with darker skin. Lending some external validity to this account. And it's helpful to keep in mind, I mentioned this briefly, that typically our target customers differ from us in certain important characteristics. And it's our job to find out what those characteristics are and what the differences are. I could give you some classic data showing that many people don't know some of the most basic computer literacy skills that you probably take for granted. But here's some not so ancient data that on iPhone, Safari has a 90% market share. And on Android, the native browsers, Chrome and Samsung Internet, depending on which manufacturer you buy from, have combined an 89% share of browser usage. And it's not necessarily that the default browser is the best one. And I'll bet many people in this room have never seriously considered using a non-default browser. So we can't expect that our customers are going to tune the defaults or even investigate changing them. And we cannot infer from non-usage of defaults or non-changes in settings that everyone's happy with what we're offering. We have to go out and investigate that. Many people don't know how to change the settings. If they do know how, they don't necessarily know how the device will perform when they do change the settings. They often assume that changing the settings could cause bad things to happen. And they often assume that whoever chose the default settings knows way more than they do. So these various assumptions that many customers reasonably make limit the usage of these various settings to a large degree in most sources of data that I've come across. Okay, so that's two stories illustrating why it's very important for us to understand customer heterogeneity. And next, we're going to get into a little bit of math, talking about how we're going to do that. So the two approaches that we're going to step through in our script, I'm going to call heterogeneity by customer attributes and heterogeneity by segment. A customer attribute is going to be similar to a product attribute. It's going to be something about a customer that we can measure. So in our smartphone data, we have customer attributes like gender, age, height, hand size, how many years ago they bought their phone. That's a behavior at the customer level that we could measure and interpret. There's a third approach that I'm going to name and give some voice to called individual level demand parameters, but we're not going to implement that in our script. It's a little bit too complicated. It would crowd out too much time from other things. So before we add heterogeneity to the model, I'm going to give a 5-minute review of the multinomial logit model, or maybe this is 3 minutes. I hope you'll recall we have this market share function for product J and choice occasion or market T. The predicted market share is going to be the exponentiated mean utility, which will be a function of the product attributes, xjt, the preference parameters on those attributes, beta, and then we'll subtract alpha, which is the price sensitivity parameter, times the price. And then we'll take that same exponentiated mean utility, add it up across all products in the market, and put that in the denominator. And by doing that, every market share will have the characteristics of a probability. They will all be non-negative, they will all be less than 1, and collectively they will sum up to exactly 100%. And the reason this is such a powerful model is that given any change in product attributes or price for any product in the market, the model gives us specific quantitative predictions about how all other product market shares would change. Model has 5 main limitations that I talked about. The first one is that it assumes all customers have the same beta and that all customers have the same alpha. And plainly, this is a limitation because people differ in what they like, call that fit or match value, and people differ in how sensitive they are to price. The third one is a little bit trickier. The model's predictions assume proportionality. So when one product's market share changes, it draws from other products' predicted shares in proportion to the sizes of those shares, which its degree of unrealistic its lack of realism comes from the fact that when one product is improving its share, it's typically going to draw from nearby products in the attribute space rather than proportionally from all products. Adding heterogeneity to the model is going to reverse these first 2 limitations and substantially alleviate this third limitation. Finally, the fourth one is it requires exogenous price variation. Heterogeneity is not going to affect that at all. We will still require exogenous price variation. And finally, the specific distribution of the epsilons is very convenient, but it's also quite unrealistic, specifically in the assumption that the draws are all independent across people and products and choice occasions. So heterogeneity will not affect these final 2 limitations. So I added this year, see if this is helpful. We can take 2 approaches to enriching this model to allow for heterogeneity and preferences. The first approach is we can make assumptions about what the heterogeneity structure is, and then we can estimate parameters within those assumptions. In the second approach, we can seek to minimize the assumptions that we have to impose, and we can seek to learn the structure of the heterogeneity from the data. In an ideal world, you might prefer to learn the structure from the data. However, it's very demanding of the data. We often won't have enough data that will enable us to meaningfully learn a heterogeneity structure. So that's why both approaches exist, and they can differ empirically depending on the characteristics of the estimation data set. So I'm representing the base multinomial logit with this inner circle. We've already covered that. That's why I scheduled the quiz in week 4 to encourage you to brush up on that and fully understand it before we extend it and add more on top of it. The heterogeneity by customer attributes, we're going to have to decide what attributes to put in and which parameters to estimate. That's something that'll reflect assumptions that we make. On the other hand, we can do heterogeneity by segment, which will involve less restrictive assumptions on our part. And the data can decide whether how different the parameters might be between segments. And then outside of those, more complicated than that, strictly more general, we can assume a distribution of individual heterogeneity parameters and then estimate the hyperparameters of that distribution. Or we can try to learn the distribution from the data, which again it's the most flexible, but it's also the most demanding of the data. We're often not going to have enough data to do this. So we'll go through this inner circle, and then we'll briefly talk about this outer circle, but that's only going to be 1 or 2 slides. So heterogeneity by customer attributes. So we're going to represent a vector of customer attributes, W. It'll be specific to each person, and it may be specific to each choice occasion, or it may be constant across choice occasions within a person. And that's going to have distribution F, capital F. And instead of assuming all customers have the same beta and alpha, we're going to decompose those parameters into a weighted set of the W attributes. So for example, say we had 5 product attributes in the model, and say we have 2 customer attributes, then this delta matrix could be as large as 5 by 2 with 10 total parameters for us to estimate. Or we could decide that we're only going to try to estimate certain elements within that delta matrix. So after we make this assumption to replace alpha and beta, we're going to be able to rewrite utility as a function interacting the x's and the w's and the price. And then we can integrate out the epsilon terms at the individual level, just like we did before. And then we can integrate the individual choice probabilities across the distribution of the w's. And then we can approximate that integral using a Riemann sum. So that's what this congruence operator or expression on the right-hand side is. You don't necessarily need to even remember your calculus about how a Riemann sum works. If you do, that's great. Your calculus teacher promised you would use it someday. Here it is. Now, the thing to notice here is that the number of parameters that we could estimate in delta or in gamma is going to be the size of the product attribute vector times the size of the customer attribute vector. So if we have a lot of product attributes or a lot of customer attributes, the number of parameters to estimate could get large really quickly. And we call those noise parameters. And so we're often going to restrict our decisions of what to put in and which parameters to estimate to try to avoid adding too much noise to the model. Does anybody have any questions about this approach? Does it seem clear? Great, okay. The second approach that I need you to understand that we're going to code is called heterogeneity by segment. So what we're going to do here is we're going to index our segments using lowercase l, and we'll have capital L total segments. And in practice, when we code this, we're going to use those 3 customer segments that we defined in the week 3 script based on the 6 usage variables. But in principle, this could generalize to any number of segments. And consistent with our discussion of what segments are, we're going to assume that the customer preferences are homogeneous within each segment and heterogeneous between segments. And based on that, we're gonna replace our homogeneous beta and alpha with segment-specific beta parameters and alpha parameters. We can then calculate the market shares within each segment using nearly the same formula, except with segment-specific beta and alpha in place of homogeneous beta and alpha. And then to get an overall market share, we're gonna add up, we're gonna do a weighted sum of segment sizes times segment-specific market shares. So we do have some choices to make. That is, how many segments and which customers are in which segments. But overall, I think it's fewer total choices to make, since we don't have to decide which attributes to put in or leave out. And we don't have to decide which delta or gamma elements to estimate or to restrict to 0. And similar to the prior approach, if we let the number of segments become really large, we're going to get a whole bunch more parameters to estimate. And so we will have a clear downside to adding too many parameters to the model. Does anybody have any questions about this approach? Does it seem reasonably clear to you?
A very simplified way would basically always just like we're just separating them into groups that conduct the same thing as one thing. Because we're just segmenting all the persons and then having those groups be homogeneous.
Homogeneous?
Yeah, homogeneous. Because I should understand like why we need to be so heterogeneous. Like, why are we individual groups? Like, why is that?
So let's take a market where just about everybody buys stuff. But we know that there are some gender differences and preferences. So let's say we're estimating demand for soda. And certainly there are lots of women who buy the full sugar soda, and there are lots of women who buy the diet soda, and there are lots of men who buy the full sugar soda, and lots of men who buy the diet soda. But the mean purchasing rate of diet is probably higher among women than among men overall. And so you're going to have some differences in the betas. You might have some other differences in the alphas and some of the other product attributes. You could imagine taking the soda market data and partitioning it by gender and estimating the multinomial logit model within each gender's purchases of sodas, and then comparing the alpha and the beta parameter estimates between the two sub-markets, right? You with me on that so far? This heterogeneity by segment is similar to that idea, but you're estimating it simultaneously. So you're positing that there's a certain number of types of customer in the market, and you're allowing the preference parameters to vary across those types. But by saying there's a type, you're saying within that type, the preference parameters are the same. So that's what we're doing in this approach. So it's sort of fundamentally different between customer attributes and segments, but they are not incompatible. We can do them at the same time. And in fact, we will do them at the same time in today's script.
So if we were to like instead separate the original data based on gender and then run the MNL like separately, it would get the same result as this one?
Generally speaking, yes. There could be some minor differences depending on the properties of the data that we use. But in theory, it should get the same result. Okay, so the third approach, which I'm going to ask you to try to understand conceptually, but we are not going to implement in our script, is called individual level heterogeneity, where each individual person could have their own alpha and their own beta vector. So here, the number of parameters to be estimated is going to be, could be as large as the number of people times the number of predictors in the model. So that could get really, really big really quickly. When we do that, we take a similar approach to before, where we calculate individual level choice probabilities, integrate out over the distribution of the individual heterogeneity. Now, what we usually do is we assume that distribution to be multivariate normal. It has some good properties, so it's relatively convenient. And then we estimate what are called the hyperparameters of that multivariate normal distribution. So capital theta would include the means and the covariance index of the parameters in the multivariate normal. Now, that assumption that the distribution is multivariate normal, very convenient, but it can be a very strong assumption in some cases. And so sometimes we may seek to relax that assumption and learn the distribution from the data. And so if we really have a lot of data, we don't have to make this assumption. We can estimate each individual customer's alpha I and each individual customer's beta I. But we need a lot of data for that. So the two settings that I've seen that done most often are in grocery purchases, where you have, say, several years worth of shopping trips and purchase data for a single household. And also in really thick digital settings, say, if someone is visiting a service or using an app multiple times a week, then you might have enough data to estimate that individual person's preference parameters. But even though this is possible to do, it's really quite rare that it actually gets done. Because the numerical improvements of estimating the full distribution, they're often limited compared to the computational costs of estimating that full distribution. So it's really only if we're going to try to go to full personalization that we'll go to all the trouble to do this.
Would that be better for like business to business, like markets? Since you would have like you will have less customers, but you would have like a long relationship with them.
Yeah, the relationship length is going to be the place where it may be possible. Yeah, I share your intuition. If you have like 3 or 5 key customers, understanding the individual customer needs will be really paramount, and you wouldn't want to assume a particular statistical distribution. Yeah. So with a limited number of customers, our computational costs will be pretty limited as well. It does depend on the B2B market. So we've talked about 3 different paradigms for adding heterogeneity to the demand model. And what I want to spend a fair amount of time on is trying to develop your understanding of how we make this type of decision in practice, because it is a really critical input to the ultimate value of the modeling exercise. And it's usually not something we can prove that we did optimally. We're often balancing multiple competing criteria when we make the choice of what model we're going to estimate. And there's a bunch of quotes here. The one I really like is scientists agree that no theory is fully correct. Thus, the real test of knowledge is not truth, it's utility. That's the guy who wrote *Sapiens*, a really famous book. Kind of a weird book. I'm not necessarily endorsing the book, but I am endorsing this quote that we don't evaluate our modeling choices by correctness, because every model is, by definition, is incorrect. Like, we call it an assumption because it doesn't always hold. If it always holds, we would call it a law or a regularity. So every model has assumptions. Every model is intentionally simplified. Therefore, every model has blind spots and degrees of incorrectness. But the question is, what can the model do for us? That's why we estimate models. They can do things for us. They can help us. And you can summarize the next 15 minutes quite succinctly by saying we should evaluate models using criteria motivated by the reasons that we're modeling. And in customer analytics, typically our purpose of modeling is we want to increase our profits and offer customer value. So those are the criteria by which we should evaluate our models. So we're going to build back up to that conclusion. That's the conclusion up front. Let's see if you can apply it. Suppose you graduate, congratulations, you join a firm. On your first day, your boss gives you a data set, and the data set represents heights and weights of a sample of people and says, I need you to build me a model. And one of the first decisions you're going to make is, are you going to model weight as a function of height or height as a function of weight? And why? What would you do?
I would model weight as a function of height.
What?
Because it looks like in this data set, there are a lot of people that share a similar height but have a different.
Yeah, so height is going to be measured on a more diffuse grid, points. So probably inches and quarter inches or half inches rather than fully continuous measures. And so how does modeling weight as a function of height relate to that observation about the height variable?
Maybe there's no supposed to be intuition.
I'd say since as you gain height, you have to gain some amount of weight too, but if you gain weight, that doesn't guarantee you gain height. Like in the real world, I think that it's kind of like it's a height to weight relationship. Just in practical application.
Okay, this is a theory that many people share, that height drives weight more than weight drives height. You know, unless maybe they're babies, or unless maybe they're 80-year-olds, which they could be, we don't know. It's not in this data. And theory is absolutely one of the criteria that we use in evaluating and determining what model we estimate. Absolutely, it's one of the criteria. How many people would model weight as a function of height? How many people would model height as a function of weight? Why would you model height as a function of weight? How many people don't know what they would model? Which way they would do it? What's the uncertainty stopping you from giving an answer?
I think I would model weight as a function of height because height, like if we're assuming these are all adults, height is like a fixed variable or like it's fixed and weight can vary depending on. Yeah, like the weight is what varies and you could have someone who's like 68 and then be 120 versus 170.
Are we certain that this is humans? Because it doesn't actually clarify anywhere on the chart. So that makes me think maybe there's some other sort of.
I did say they're people, so that's safe to assume here. So many people have this intuition that humans can control their weight, at least to some degree. So weight is maybe more malleable and it's more driven by height. Of course, that's not always true. And that causal ordering is not necessarily relevant to the purpose of our modeling. So I would flip it around, you know, the fact that you more often get multiple weights within a height makes it harder to get a unique weight for any given height. So if your goal is a really precise prediction, you might want to model height as a function of weight. And recall what we talked about in week 1. If your goal is prediction, you do not necessarily need causal analysis. Correlations can be very, very predictive. So in my opinion, the reason this is a hard problem is because we haven't clarified what is the purpose of the model. We should evaluate the model by what it can do for us. And so if we haven't decided or we don't understand why we're modeling, it's very hard to make and justify modeling choices. So depending on what the reason that you want to build this model, you could build an argument for height as a function of weight or weight as a function of height. And the strongest argument, in my opinion, for weight as a function of height is that theory about causal ordering, and the strongest rationale for height as a function of weight is the relationship between the variables. The fact that height is more discrete. And so using a continuous variable to predict what's essentially a latent function with discrete levels is often empirically more accurate than vice versa. So the modeling trade-off that commonly gets taught, although many people don't fully understand it for a long time, is the bias variance trade-off. The more we faithfully represent the data in our model, past some point, we start to lose ability to generalize to non-trained data. So if we seek to minimize bias, we tend to have more variance than if we seek to balance bias against variance. So OLS is, you can prove, right? It's blue, it's the best linear unbiased estimator. Best in the sense that it trades off both bias and variance. The analogy that I find helpful in thinking about this is like, suppose you prepared for the quiz by simply memorizing every single word in the course. If you memorized every single word in the course, and then you got a quiz question that required you to apply the concepts in an unfamiliar setting, you might not have the understanding necessary to create that application. You would have minimized your bias, you'd know your data exactly, but you would have a hard time generalizing that knowledge to non-trained settings. So what most estimators seek to do is to make some trade-off between bias and variance. So R-square is our most common way of measuring fit to the training data. And if your goal is to maximize R-square, you're often going to sacrifice variance in the process of doing that because of the bias variance trade-off. So let me tell you a story about that. This story is about a hypothetical business economics major, graduated and went to work for went to work for a startup that had 2 quarters of sales and pricing data. And so as she learned in MGT 100, she standardized the price and the quantity data, and her job was to estimate demand. And so she estimated demand and it slowed down and she got an R-square of 100%. A plus. And she went to happy hour. And then another quarter went by and they got a 3rd data point with price quantity. And when she estimated demand, it didn't fit any of the training data. But she noticed that if she added a quadratic term to the model, she could fit all the training data perfectly. And yeah, it's upward sloping in one part, but we're just, we didn't mention that. We just graphed the last part. R-square 100% A plus. Let's go to happy hour. And then another quarter passes and we got a 4th data point and our linear demand model doesn't fit and our quadratic model doesn't fit anymore. And so we add a cubic term and it's downward sloping in the central part of the data. R-square 100%. Where are we going? Going to happy hour. And then many quarters later, we learned that the relationship between these 2 variables is actually quite weak. And everything we've started doing was overfitting the data. And really wasn't a useful exercise. And this is illustrating the trade-off between bias and variance. If we fit our training data exactly, to some degree, we are fitting the randomness that is incorporated into that training data. And we don't want to fit the randomness. So please do not think of R-square as anything like a grade or a correctness. It is something to consider in conjunction with other quantitative measures, but it is not something to maximize. So the bias variance trade-off is something we can quantify, and I'm going to introduce how we quantify the variance part of that in a couple minutes. But it's not the only thing that drives our decision of what model to build and how. We also have some other perspectives. So why are we modeling? The model's performance on our objective function is if there was one single thing, this should be the most important one. The theoretical properties of the data generating process or the model also influence our choices. The rigidity or the flexibility of the model is something that we should consider. The multinomial logit is less flexible than the heterogeneous demand models that we talked about a few minutes ago. You probably have some prior modeling experience, or we may have access to people who do, or we can read papers by people who have made similar choices. And we should take all of that into account because we may learn something that helps us model better. And the computational properties of the model as well. So In order to quantify the predictive performance of a model, we're going to talk about something called cross-validation, which is a procedure that is an example of what we call retrodictions. So retrodictions are when we use a model to make predictions after the fact on non-trained data. And we can quantify the model's performance to accurately predict the data that we've held out of its training. So cross-validation is the most famous way to evaluate retrodictive performance, not the only way. And we do want to be careful. Retrodiction is not the same as prediction. Prediction means the data haven't been created yet. We're predicting the future. Retrodiction means we have the data. We're just holding it out of the training process and then evaluating the model's generalizability to the non-trained data. And the difference is that the data generating process may change in a fundamental way in the future. Whereas after the fact, we usually know if it's similar data or not similar data. So cross-validation is going to be a pretty intuitive algorithm, I think, for most people. We're usually going to compare a range of models on their retrodictive performance. And so we'll index those models with little m. And this could be different specifications within a single model, or it could be different types of model with the same predictors, or any combination of predictors and models. And so we're going to take our training data and we're randomly going to divide the points into capital K distinct, we often call them folds. I think partitions is a little bit clearer. You can also call it subsets. The key is that they're not overlapping. And what we're going to do is we're going to estimate each model K, capital K total times. With each estimation, we're going to hold out one fold. And then we're going to use the trained model to predict the non-trained data that we held out. And we'll do that for each fold, for each model. And then we'll be able to calculate a prediction error. Usually it's minimum absolute prediction error or mean square prediction error. Not minimum, it's mean absolute prediction error or mean square prediction error. And then we can compare that across all of the models to see how much they differ. And so this version has a picture to kind of visualize this process. If we fix capital K to be 4, so we're operating within quarters of our data set, we're going to estimate each model 4 times. And then each time we estimate it, we'll hold out 1/4 of the data and then use the trained model to make predictions within that held out quarter. And we can even increase this all the way to set the number of folds equal to the size of the data set, so that we're only making 1 prediction each time we estimate the model. And thereby we can quantify the variance component in the model's predictive performance. Now, another way to quantify this is called a non-random holdout evaluation. And basically, if the data has changed in a meaningful way in the past, you could estimate a model up until that change, simulate forward what might happen after the change, and then you can compare different models' predictive performances when the data generating processes change in meaningful ways. This is a non-random validation test, tends to be a much stricter criterion. We're not going to be implementing this in class. I'm just naming it so that you have some understanding what it is. In this paper, what we did was we took 30 years of data for the entire automotive market. We estimated models of automotive model quality and pricing. The the training period ended in 2007, right before a really large gasoline price shock in 2008. Then we simulated qualities and prices going forward after 2007, and we found the micro-founded models predicted changes in car qualities and prices better than non-micro-founded models. I say that mainly because it took us a decade to write this paper, and I want to feel like it benefits someone. So if you didn't get any of that, that's okay. I won't twist you on that, I promise. Okay, we're going to take a break in just a minute. The main thing I want you to understand, sometimes people feel a little uncomfortable using individual customer attributes in a demand model. And you should feel some discomfort, I would say. Because there are risks to it. They're real risks. If you're working in a startup and you misuse customer data and that can be detected externally, that can kill the startup. One lawsuit can kill a startup. A lot of startups are not capitalized well enough to defend themselves against one well-founded lawsuit. The principle I would offer is if you are using customer data in a way that both legally and genuinely serves customer interests, you're probably going to be fine. This gets a little slippery because the word genuinely, who's to say, right? If you have motivated reasoning, you may come to a definition of genuinely that you might not if you were outside the company. But generally speaking, this is a reasonable guiding light. If you're using customer data against customer interests, you probably should be concerned not only about the ethics of what you're doing, but also about the potential consequences, because you're sort of inviting your customers to retaliate against you. Okay, you've done a great job of staying with me. I appreciate it. Let's take 10 minutes. We'll resume at 3:25 and we'll step through our script. Yeah.
Sure, Shit, you know, was pretty. Well, that's just, I think that was like very bad. I think they're pushed back. You saw this. I haven't had like, I haven't felt that.
Yeah, it's good.
You thought it was mine because I water on my. I was like trying to smell it. Like I should. Yeah. Yes, thank you. We can.
Was you guys I talked about this one last month or meeting with United? Did I see this before? Where your plants is weekend.
Never reached a qualities restaurant.
Oh.
Somehow it's the best cuisine, my personal opinion. Out of a lot of cuisines, there's only one in the county in Oceanside.
I see it. What suits your fancy?
Everything, nasi goreng is kind of a staple, but. Otherwise, just preparing the gate. But why not? It's so good.
Restaurants, like, or not.
Where are you from?
I'm from like San Bernardino, it's like very used to the other side.
Oh, yeah.
There's the prices.
I don't know about this year, last year.
Like, I think it's like John Nashville, like. I go
I was like, guys got on our side as more disease.
I used to wrestle too. Oh, yeah, that's what I was thinking. Yeah. You just don't have polyphone.
Yeah.
That's good, that's good. I mean, me too.
The earphones, some of my buddies give us. Be like in the tank shops and stuff like that.
I think, like, I know it's shower, you know, everyone, like, I see them, like, I just want to shut up.
His name was that. They see there's some things from like this, and then they released the whole
What years? High school. High school.
Yeah. Tiny and high school. The reason I would have been when I was in high school, I mean, like my freshman year, I was probably like I'm 3.
Okay.
I'm like 6'1" now.
Yeah. I'm about to say, you don't work.
Yeah. No, I was 13. Then I think our Russell was like 126, 32 when I saw it 3 years ago. I did 145. Refreshing. Yeah. Sebastian. Yes.
But, oh,
Yeah, I don't know. So you got on toes.
Yeah, mine might have that. I'm not sure if you, I got mine from just like that. Like,
Yeah. I had a son that I was trying to go with really nice. Years ago, jiu-jitsu. And so I have like one man coming up trains to see me this weekend. I'll be like, I know, I try out to. Yeah, that's right. That day, dude. I don't have any car.
I used to all the time. Like you think the like I can't go back in.
And consider. That would be. I don't know. That's how it's been done.
Okay, so we're gonna step through our script and then after that, we're gonna talk about contracts. So I hope you've got the script open. You know, depending on your operating system, you might, it might want these double dots for the home directory or not. On Linux, it really likes these, but on Windows it doesn't. So we're gonna load in our, you know what, I am first just going to get rid of all my dots in the last, and then I'm just gonna run the entire script and hopefully it's gonna work. Create everything I need on this shared computer up here. And then after that, I think I'll have everything to get the week 5 scripts rolling. Um, so, I mentioned that, the number one criterion for evaluating a model is, its performance on the reason that you're evaluating it, on the reason that you're using it. And so when we're adding heterogeneity to our demand model, one of the things we really want to pay attention to is how do predicted market shares change when we put heterogeneity into the model? And so we're going to do two things to pay careful attention to that. First, we're going to graph the heterogeneity in predicted market shares. And then secondly, we're going to estimate a range of heterogeneous models to show that resulting heterogeneity in predicted market shares. So the first thing I'm going to do, starting on row 63, is I'm going to create a function which is going to plot the distribution of predicted choice probabilities in the market. And then I'm going to re-estimate this homogeneous demand model that we saw 2 weeks ago. And I'm going to use that homogeneous demand model in this new function that I made. And so what you see is degenerate distributions of choice probabilities because the homogeneous demand model assumes all customers have the same preferences and therefore have the same choice probabilities. And as we add heterogeneity to this, as we add heterogeneity to the model, we're going to stop getting degenerate choice probabilities and we're going to start getting histograms of choice probabilities across people. So we're going to be looking at the implications of different heterogeneity representations within this structure. And if that didn't all totally make sense just yet, I think it will as we go. Now, one thing to notice is that we've got an x-axis, which is in the probability space going from 0 to 0.6, and a y-axis in the count space. And these are going to be histograms. They already are histograms, but they're degenerate histograms. And so the height of the bar shows how many people are currently receiving a discount for each of the 6 phones in M.1. And the x-axis shows the model's predicted choice probability for those people when they have that discount available. The choice probability of A1 when they have a discount available on the faceted phone. And the reason that these bars currently have different heights is that the discount frequency is not the same for all 6 phones. Like you can see, Apple phones were discounted less than Huawei and Samsung phones. So that's why you see higher bars for Samsung and Huawei, is there are more discounts in the market. Okay. So the first method of adding heterogeneity is by customer attributes. The most important customer attribute is going to be customer need. We don't have that measured directly, but a good proxy for it that we've talked about before is how many minutes people use their phone. Should be driven by core need. And so the first attribute that we'll add to our model is going to be weekly minutes of phone usage. And so I'm going to plot the histogram of weekly minutes of phone usage. And it's unimodal. It's skewed a little bit more to the left than to the right. I wouldn't call it a symmetric distribution. At least not with those thick bins. Yeah, so if we thin the bins, it looks like a little thicker on the right-hand side than the left-hand side. But a normal wouldn't be a bad approximation. So now I'm gonna first only add customer attribute interaction with price into the model. And I'm gonna enrich a model gradually so that I understand the implications of each enrichment that I consider. And so we can look at how much this one interaction between a product attribute of price and a customer attribute of minutes of usage, how much it changes our various model diagnostics. So our previous model diagnostics were product hit rate of 26%, likelihood ratio of 0.0409. And now we're getting a product hit rate of 28.7%. It's a pretty substantial increase, actually. Likelihood ratio of 0.0530. Okay, so the measurables improved a bit, so it's probably gonna help us predict better. And then let's take a look. Now, instead of A1 having those degenerate choice probabilities when each of the 6 phones is on discount, now we get real distributions of choice probabilities across people. And if we look at the pattern of the parameter estimates, well, before I really go into it, I think what I would expect is that someone who uses their phone more should be less price sensitive overall. Because, yeah, they're going to get more value out of what they pay, so they should be more willing to pay for a phone. And so our price sensitivity parameter before was negative 0.0698, okay, highly significant. And now that intercept, the comparable parameter is much larger. Well, in absolute value. And then the interaction is positive, meaning that people who use their phone more will be predicted to be less price sensitive on average. Both of those are highly significant. And so what that suggests is that this distribution of choice probability of how the prediction of someone buying Apple's small phone responds to a discount on Apple's small phone, the higher minutes people are probably going to be up here on the right-hand side, the lower minutes people are going to be on the left-hand side. Now, some of the other phone distributions show more of like a single-sided distribution in choice probability. And that's because, do you remember with that beach example, there was always going to be that indifferent customer in between the two vendors, right? People bought from the vendor closest to them. And that's basically what's going to be driving these one-sided distributions. We're graphing the probability of choosing A1, and there will be some point where everybody above that point is better off buying something else. So that's why we get more of like a regular looking distribution, a two-tailed distribution on A1, and more of one-tailed distribution. And we can really kind of dig into this a little bit if we want to, which is kind of what we're going to do next. So we're going to pull out 2 individual customers, and we're going to calculate their individual probabilities to really kind of illustrate what's going on underneath the hood of the model. And so the first customer is ID number 2, and their second customer is ID 31. And I'm picking those 2 specifically because they have quite different minutes of usage. And so You can see that in the estimation data by price times minutes being quite a bit larger for customer 2 than it is for customer 31. And you can also confirm that by going back to the original customer data and pulling out rows 2 and 31 and comparing the total minutes. And so customer 1 has about 35, 40% more total minutes per week than customer 31. And so if we take the coefficients out of L5, which is our heterogeneous model that we estimated, and then we calculate the fitted residuals for each, or I'm sorry, the X beta hat for each of these 2 customers, and then we apply our multinomial logit choice probability formula, which is exponentiating that X beta hat and then dividing by the sum of the exponentiated X beta hats in the market. What it's going to say, remember, customer 2 was using a lot more minutes than customer 31. Customer 2 is on the first row here. And so customer 2 has much higher probabilities of purchasing the phones that tend to be more expensive, the Samsungs and the Apples, whereas customer 31 has much higher probability of purchasing the cheaper phones, the Huawei's. So this is basically how the model is generating the individual level predictions that lead to these distributions that are graphed in the illustration. How are we doing? Yeah.
That's not just. One. Or is that not?
So in the formula, what we're graphing is when each phone in the market is on discount, what is the model's distribution of choosing A1? We could alternatively graph the model's distributions of choosing S1, and then your intuition would apply exactly. We would get a 2-tailed distribution in the S1 facet, and then 1-tailed distributions elsewhere. Does that answer your question? I didn't want to go to the full 6x6. That'd be a lot to look at. So, okay, so that's how it's operating underneath the hood. The next thing I want to do is to estimate a range of heterogeneous demand models. And I'm also going to estimate the same homogeneous demand models we saw 2 weeks ago for comparison. So the first model we started with just had brand dummies for Apple and Samsung. And that's out 1. So we're keeping the numbers, the output numbers consistent. And if I interact Apple and Samsung with our segment identifiers, so this is adding heterogeneity by customer segment. Let's take a look at what happens. So in our homogeneous model, Apple's brand intercept estimate was 0.15 and Samsung was about 0.25. And our overall product hit rate was about 26%. When we make these brand intercepts heterogeneous, what we find is that segment 1 doesn't like Apple as much. They like Apple less than Huawei, which is the reference brand, and they like Samsung more than Huawei. Segment 2 really likes Apple a lot and likes Samsung more than Huawei. And then segment 3 is almost indifferent between Apple and Huawei, but has a relatively strong preference for Samsung. So we're seeing 3 different patterns across the 3 segments. Now, these differences are not all statistically significant, but some of them are to varying degrees. And our product hit rate, it was about 26% before, it went up to 28.2% by giving the model this extra information about customer differences. Now, I can use that heterogeneity by segment, and I'm going to show how it leads to variation in choice probabilities in our familiar graphic. And remember, the underlying assumption in that approach is that there's certain types of customers in the market. And in this case, we have 3 segments. So it's like saying there's 3 types of customers. And that's why we get these 3 bars in our distribution of choice probabilities in response to discounts. And across the 6 phones, 2 bars are very close to each other and 1 is farther away. And if you remember, we had 2 segments that were relatively larger and a 3rd segment that was relatively smaller. And so it looks like that smaller segment has some similarity to one of the 2 larger segments, whereas the other larger segment is less similar to these 2. Okay, so our next model adds price in, and so we'll do out 2 as our homogeneous version, and out 7 as our heterogeneous version. And let's focus on price. We had, so out 7, we're going to be interacting with the brand intercepts and price with the segment indicators. And previously we had negative 0.0059 as a price coefficient. And now what the model is telling us is that segment 2 is going to be the least price sensitive, whereas segments 1 and 3 are similar in their price sensitivity. And segment 2 is the one that really likes Apple. After we control for price. Segment 3 looks like it values Apple and Samsung similarly. Segment 1 likes Apple a bit more than Samsung. And our product level hit rate went from 27% up to about 28%. Now, something kind of interesting here. Model 7 is a strict generalization of Model 6. So here's Model 6. We have brands interacted with segment indicators. And our product hit rate is 28.2. Model 7, we add price and interact everything with segment. And our product hit rate actually falls a little bit. Not by a lot, but from 28.2 to 27.98%. And when you look carefully, you're going to see this type of thing happen a few times throughout this exercise. And the reason that it got worse is that we have 2 segment level price interactions that are almost identical. It's like giving the model 3 parameters that are hard to distinguish from each other. And this is an example where over-parameterizing a model can worsen its performance. So we have to be careful on this bias variance trade-off. But I'm pretty confident that that's actually going to change once we give the model product level intercepts, which really helps it distinguish between products within a brand. And similar before, we have this 3-point discrete distribution where two of the three segments look very similar to each other. All right, our previous series of homogeneous demand models next supplemented the model using screen size. And here we're getting to our product hit rate of just a little bit better, 27.08. And then when we add that into our heterogeneous demand model, interact that with segment, we're not improving very much over what we had before, which was similar to what we saw 2 weeks ago. But we are getting a little bit more separation for A1 at least, because if you take a look, you're going to see that there is some difference in segment valuations for inches of screen size. And finally, with our next model, we're going to now include an interaction between customer segment and customer minutes of usage. So this will be the first time we combine our two approaches to incorporate customer heterogeneity. And we're starting to get a lot of parameters, so they're not always going to be super easy to interpret. But it does look like there are some important differences between the segments, where it looks like segment 3 is going to be the most price sensitive. And then this last set of interactions includes screen size, and screen size will make the biggest difference to segment 3's price sensitivity. So then when we look at the product hit rate, what's going on here? This time it improved up to 28.9%. And when we look at the model's distribution of predicted choice probabilities, we've now got a mix of mass points and tails. Okay, and then model 10 is going to be the first time that we incorporate phone dummies. And those made a big difference in our homogeneous demand modeling. And if we were to judge that using product hit rate, we're up to 29.2% in the heterogeneous demand model. And if we look at our distributions of choice probabilities, it looks like they're becoming the most diffuse that we've seen yet. Now, at this point, we're going to add 2 more extensions to this model. They're both, in my view, a little bit gratuitous. So first, what we're going to do is we're going to interact. We previously had product segment interactions in model 10. And so now in model 11, we're going to have 3-way interactions between product segment and individual user minutes. And so we're adding a whole bunch of parameters. And what happens, our product hit rate falls. Doesn't fall a lot. Falls from 29.3 down to about 29%. And our distributions, the y-axis keeps rescaling. So it may not be super obvious, but these keep becoming more diffuse. And then in our last heterogeneous demand model, I'm going to do something intentionally that I know to be dumb. I'm going to treat each customer identifier as if it were a customer attribute. So these identifiers came from the rows of the original customer data set. So the customer on row 1 is customer number 1. On row 2 is customer number 2. And I'm gonna act as if that's information about the customer's preferences, which I know that it's not. And interact those. And then what happens to product hit rate falls to 28.8%. And then we get almost a flat distribution on the probability of choosing A1. Sophia, are you with us? Doing something else? You can do something else just silently so you don't distract other people around you or me. So by incorporating something that I know not to be a real indicator of customer needs, I've brought in almost like a flat distribution of customer choice probabilities. And when we evaluate cross-validation performance of each of these models, that's where that's going to really show up. So that's what we're going to do next, is we're going to define this function to calculate. First, we're going to set the number of folds to be 10. We're going to estimate each of these models 10 times, holding out a random 1/10 partition of the data. We'll predict what the model didn't see. And then we're going to calculate mean square prediction errors for each model within each fold. And we're going to graph those. So we estimated 12 models. We calculated cross-validation mean square prediction errors for each model using the same data every time. I'm going to arrange those results into a table and use ggplot. And if you recall, models 1 through 5 were the homogeneous models. Models 6 through 12 were the heterogeneous models, where model 12 was the one that I intentionally sort of sabotaged by treating customer index as if it were an attribute. And so for models 1 through 5, as we gave the model more information, it predicted better in non-training data. Starting with model 6, we compare that to our baseline model 1. The heterogeneity helped the model to predict out of sample better. And the same is true for the analogs for models 1 through 5. Models 6 through 10 all generalize to non-training data better than models 1 through 5. When I added those three-way interactions between segment and minute and product, model 11 is slightly better than model 10, but it's not really worth it, in my opinion. So I'm going to prefer model 10 over model 11 because model 10 is much simpler. And then when we intentionally added a noisy attribute in model 12, even though it had all the information that was in model 11, its cross-validation performance significantly deteriorated. So this is sort of the flip side to R squared. When you improve a model, you're often going to improve its fit to the training data and its ability to generalize to non-seen training data. However, there will come a point where you're going to hit a frontier and further improvements to training data fit will start causing the generalizability to suffer. So what I'm going to invite you to do in this week's competition is to try to find a new combination of customer attributes and product attributes that maximizes the likelihood ratio stat, and then evaluate that model's cross-validation performance. So this is going to have an objective correct answer. I don't know if a lot of people are going to find it. If a bunch of people find the correct answer, then we may not have any winners, because to win, you have to stand out from the pack by definition. So we'll see how this goes. You might be able. No, yeah, okay. I shouldn't give any hints. Okay. So that's going to wrap up our script. There are two main things left that I want to do. The first one is go through some good evidence on how demand model choice and specification of predictors affects its performance. And I think this example is a little dense, but it illustrates the difference between evaluating a model using objective criteria versus statistical criteria. And after that, we're going to talk about conjoint analysis. So this paper was published by a couple of academics. One of them is went on to work at Google after that. The question is very germane to what we're discussing today. It's how do we decide what model we should estimate, and how do we decide what training data we should include? And so they're going to evaluate that decision for a range of models and for three different sets of training data. And this is actually a pretty hard problem that they're going to apply their demand model to. They're going to try to come up with individual shopper predictions of how those shoppers would react if we give them a coupon. And so this is done in the mayonnaise category, packaged mayonnaise in like the grocery store. And we're going to use a separate data set that shows each household's typical response to coupons as a source of ground truth. And we're going to keep that outside of the model training process. So we'll be able to evaluate these models using this separate source of ground truth so that we won't be biasing our evaluation. And the key question is, if we were to follow all of the model's predictions, how would our coupon profitability depend on our choice of model and the way that the information we use to train the model? And in a coupon exercise, we have two degenerate strategies. One degenerate strategy is don't give out any coupons. Another degenerate strategy is give everybody a coupon. And so those will be very simple benchmarks against which we can compare the models. And in some cases, we're going to find that these degenerate strategies perform better than the models do. Now, the reason this is a hard problem is because we have to distinguish loyal customers from marginal customers. If you give a coupon to your loyal customer who was going to buy from you anyway, it's like you're giving away your margin. You're directly reducing your profits. Because the counterfactual of giving a coupon is not giving a coupon. They're going to buy in either case. Lowering their price saves them money. I'm sure they'll love it, but you're giving away your margin. So that's not good if you want to maximize your profits in most cases. What you want to do is you want to find the person who's almost indifferent between your brand and a competing brand, or between your brand and not purchasing anything. And that's the person you want to give the inducement. And so following a model's recommendations can worsen your situation if the model isn't well enough calibrated to distinguish loyals from marginals. And we're going to ignore the long-term ramifications in this exercise for simplicity. Now, the three sets of training data that we're going to use, the first one is going to be a fairly standard indicator of demographics. And you'll recall I've told you that those are generally not strong predictors of choices in most categories. The second one is going to supplement that with more information about the household. Some of these variables refer to the head of household's educational attainment or the household composition. And then the third set refers to the household's past purchase data, how often they've purchased the focal brand, the counts of each brand purchase, how often they've purchased on discount or on other marketing variables, such as when the product is featured in the store circular or at the end of the aisle. how much they've switched brands in the past, and how much they've spent total in the category. And so those are our sort of our training options. Now, in the demand models that we're going to consider, there's going to be a couple based on the hierarchical Bayesian logit, which I mentioned before, that assumes a distribution and then enables individual demand parameters drawn from that distribution. We're also going to include the multinomial logit, estimated two different ways, using lasso and elastic net. We're going to use a couple of purely machine learning frameworks, including a single layer neural network and a deep neural network. A nearest neighbor algorithm, which kind of says if you plot all the choices in a space, you estimate each probability of purchase by averaging within a local neighborhood of that point, and then a couple of random forests. And then all of the models will be trained using cross-validation, given that the purpose is predictive. So that way we can avoid overfitting the models. And so there are two main ways you can evaluate model training data combinations. You can evaluate it based on the modeling objective, which is profits, or you can evaluate it based on the statistical performance of the models. And I'm going to show you in a minute, those come to very different conclusions. And this always reminds me of the saying, pessimists are often right, optimists are often wealthy. Have you heard of that before? It often gets misattributed to Mark Zuckerberg. It existed before he said it publicly. But the idea is simply that if you want to be right, just predict failure. But if you can figure out the right bets to place, because most people predict failure because failure is most often right, you can be one of the few who make it, right? So you don't have to be right a large number of times if you want to be wealthy. Just being right a couple of times on the right opportunities can get you there. So first, we're going to go through the economic criteria, and this table's a little dense, so let me walk you through it. So the two degenerate strategies, profitability per shopper, is down here. If you give nobody a coupon, you make $5.50 per shopper. And if you give everybody a coupon, you make $6.45 per shopper, suggesting maybe prices are too high. Now, within the base demographic categories, I'm going to take this $6.45 as a baseline because a model should do better than something you can get without modeling at all. And none of our models, except for our heterogeneous logits, are beating that baseline when all we give them to train on is the base demographics. And some of the machine learning algorithms are doing particularly poorly. And that's not an indictment on those algorithms. What it is saying, without clear signal to distinguish loyals from marginals, they can't make that distinction. So it doesn't mean it's a bad model. It just means it's not suited for this task with this training data. Once we supplement the demographic information, some of the logits are starting to beat the benchmarks. And the deep neural network and the neural network also are competitive with the benchmarks, but some of the other machine learning frameworks are still doing poorly. And then once we train the models on the purchase history data, now most of them are doing better. The random forest is still losing to the blanket coupon, but everybody else has become profitable. And I think the logit models are doing a bit better than the machine learning frameworks, but not a large difference. So in contrast, if we were to evaluate the hit probabilities, we would not see the same differences. We would see some of the machine learning frameworks outperforming some of the choice models. And the differences would be much more muted overall. So the key point here is to try to illustrate the claim that we're modeling for a reason. If we want to evaluate models, we should evaluate them based on their utility for the purpose that we're using them for. Statistical criteria can be helpful. We do want to pay attention to that, but it probably shouldn't be primary. And then if you dig into why those extra information help a lot, it's because each household's past tendency to purchase on discount is a very, very, very strong driver of their acceptance of a future coupon. And that is true across all of the models, although their sizes do change a bit with the specification. Okay, so a couple takeaways. If you want to predict behavior, use past behavior. It's generally better than demographics. Micro foundations do appear to help demand models to perform well, even when there's limited behavioral information available. Machine learning models are great. I don't mean to criticize them in any way, but their performance often depends on how much data do we have and how good is it. And most important, statistical criteria will often not lead you to the same decisions as economic criteria.
Yeah, I thought before, we specifically said to not use past purchasing behavior, it's the like cart in front of the horse. So what is different about this statement?
Yeah, so that's a great question. I'm so glad you asked that. So when we said purchase history, so recall that when we talked about putting the cart in front of the horse, this was in response to the idea that we should segment based on customers' preferred products. And then the segmentation scheme would not be able to help us understand what would shift customers' preferences among preferred products. The heterogeneous demand model is fundamentally different because we'll be estimating how past choices relate to future choices, thereby estimating the relationship between past and future choices. So does that help to clarify?
It's just like a fundamental difference between segmentation.
Exactly. The last thing I want to do, I'm going to jump ahead. There is a link on slide 36. It's called Food in the Ballpark at the bottom. And there's a code right next to that link, 920-89, that dash matters. And at the risk of making you hungry, I want us to go through this exercise of choosing what food we would buy. So there's a group ID entry here. That's where you put 920-89. And then you'll be able to see the whole class's data in about 5 minutes. And so don't skip the questions. That's kind of important. So, okay, imagine you're at an evening baseball game. Game is halfway over, very hungry, and you leave your seat to buy dinner. And I want you to make your own choices. There's going to be 6 foods. There's going to be a waiting time. There's going to be a price. And I'll make my own choices up here. And I will not choose the salad ever. Everybody finish your choices. Another 30 seconds to wrap that up. So we're going to use this data as the heartless billionaire new owners of the San Diego Padres to decide how much to charge and how many staff we should hire. It's gonna do that for us on the back end. So yeah, so you may be familiar, Sawtooth is the leading provider of contract analysis software. And this is just a demo that they set up for clients. So I'm gonna be focusing mainly on how it's a heterogeneous demand model under the hood. But we're not actually gonna be running it beyond what we just did. So that doesn't seem right. There's gotta be more people than that, right?
You gotta click forward.
Oh, thank you. That's mine. Yeah, I always forget that actually. Okay, you guys are like me. You like pizza. Oh, garden salad. Took an L. Okay, so the directionality of the waiting time makes sense. Some of you are willing to wait. I guess you don't like baseball that much. Price. Okay, so we really don't like $11, but there's not that big of a difference between 6 and 850. Yeah, that all makes some sense. The fall off to 11 is probably bigger in the aggregate than you might expect. So now, oh yeah, they're gonna visualize it. That's what we just saw. Yeah, okay. You do some 2As, that's fine. So the 2A is when the slope really changes, then it actually matters, right? So garlic fries at $11, nobody wants it. But between 6 and 850, it's practically the same. So if you're like me, garlic fries is like the fallback, right? Like you can make do, but is that what you want for dinner? At least it's not a salad. I mean, I do like salad is good. It's crazy. It's a salad's a side piece. So, all right. So here's the thing. So this is why this is valuable. You can arrange the menu of what you offer. So if you're the new Padres owner and you say, I need to save some money to, I just financed this purchase, I'm going to let all my staff go. I'm going to raise all the prices, and then the waiting times will be maximal. I really only need to stock 4 foods. I can get rid of the fries and the salad. And what's my remaining market share? It's pretty high, actually. Like everybody's buying in this market. Nobody's skipping dinner. That's what it looks like. Even if they have to wait and pay a high price.
Do you think like results would change if the same people that did this simulation were like sat in a room in front of like a sample of each food item? Because I feel like there's like that expectation versus reality. Like of like purchasing your food, and then when you actually get it, is it like satisfactory or not?
Yeah, I think that's a very legitimate criticism of this application, is that what you say you would predict or what you say you would choose in a certain case, unless you're hungry at that moment, it may not at all be what you actually choose, right? That's going to be a revealed preference, stated preference limitation of conjoint in general. And so very much conjoint definitely has that limitation. I think that's important to keep in mind. But what conjoint does, like the reason it's valuable, is you can evaluate all sorts of hypothetical menus of options that you might offer before you actually offer those options. So there is a substantial offsetting benefit. You can calculate profits under different combinations of attributes, different menus, different wait times. And that is the key reason that this framework is so popular. There really are there are high tens of thousands of conjoint analyses studies run annually. I wouldn't be surprised if it was in the hundreds of thousands. This is really, really popular. And it's especially popular in categories where the setup cost of introducing a new product or service is high. And so, you know, you think of your smartphone, right? That was manufactured in a factory that probably cost hundreds of millions of dollars to configure. And the trade-offs that go into that product, right? There's how much memory is on board, how much battery is on board, what's the dimension of the device, what's the processor speed, how does that, these are real trade-offs, right? They can't just give you the best of every single attribute, because you're going to have like a brick in your pocket and you don't want a giant phone in most cases, right? So there's real trade-offs. So before you sink that 9-digit tooling cost into your factory, you can predict which combinations of attributes are going to max your profits. This is also really, really popular in categories with large numbers of attributes, so large attribute spaces. So deciding what types of rooms get built into a hotel and how those different room attributes interact with intangible service attributes, and then how those get priced. So this is, and you know, it's interesting, many of those decisions get made regularly. So I think it's reasonable to think that the regularity of conjoint analysis in those regular decision-making processes could be a vote of confidence in conjoint. So there definitely will be boundary conditions, but it seems to be a pretty good framework in general. You just did a choice task that didn't feel super realistic. In packaged goods, we often try to clutter the choice task in a way that makes it look similar to an actual choice environment, because those tend to be very cluttered environments in grocery stores and drugstores. In other categories, we often find that the number of attributes that we have to ask people to choose between is, we have to keep the task somewhat limited. If we make it too complicated, people will start choosing randomly. They'll feel overwhelmed by the choice task because they don't spend a lot of time making these choices unless we really pay them to, or unless we incentivize it somehow, which we do sometimes. So the approach to running a conjoint analysis study is the following. You decide the attribute space and the points within that space you want to evaluate. You try to sample a representative group of your potential customers. You typically ask them to make around a dozen choices based on a handful of attribute bundles. so that they don't get overwhelmed and they don't get fatigued. Then you use the data to estimate a heterogeneous multinomial logit model. And then you use the estimates along with projected cost data to try to optimize your product attribute locations and your predicted profits. And so I'm just going to close with, yeah.
When you're recruiting the consumer participants, are you at all being like, is it just survey where it's kind of like the volunteers who may be a skewed representation of people who want to participate, or is it you'll get this if you complete this, and then you run the risk of people just kind of trying to get through the survey or sawtooth or to get the end result?
Yeah, it's a great question. You know, you generally you should expect to get what you pay for. There's a whole range. There's a bunch of different companies that source marketing research participants. It could be as simple as they sign people up online, and then maybe they're real people, or maybe they're just even bots paid to collect, you know, provide data to collect payments. Some companies recruit real human beings in public places. Some companies running conjoint recruit participants from their own customer base. And you know, you can, you know, there are like professional research participants to some degree, people who just fill out surveys at their desk job where they have a lot of free time. And at least to the degree that you can measure individual attributes, you can try to correct for some of this, which is a pretty standard approach. But there is a cost quality trade-off in sample recruitment.
Yeah, you mentioned the professional take surveys. Wouldn't that be an issue because then they're not, they might not even actually be a customer of that product, or they might have certain biases. They're just like, that's what they do is this something like the service.
Yeah, so a lot of times when people get recruited into these panels of participants, they have multiple things that get measured, such as, are you an Apple user? Are you an Android user? And so we can subsample from within those pools of people based on relevance. So a lot of companies will try to subsample particular people, but it can be a limitation, and this speaks to, again, stated preference versus revealed preference.
The reason why period is out, but they have is it just like a time when they response?
Well, in order to, so this is helping you decide what to offer in the market before you actually need to offer it. So that's the key value of this approach is you can simulate the results of which location in the attribute space you enter at. We're going to close with a case study by Uber. Uber did a really careful job writing up how they implemented conjoint, and they did it in a really professional way. They decided, so this is back in 2013. And at the time, Uber was primarily competing with town car services, which was a pretty high margin business. So obviously, if you send one person from UCSD to the airport, that's way less cost efficient than sending two people who don't know each other in the same car. So you can lower costs dramatically, and you can lower prices if you get people to agree to share cars. And so that's what they wanted to do. However, they hadn't had much experience in the more price sensitive segment of the marketplace yet. And they didn't know which combinations of service attributes would maximize ridership. And they were really concerned, like they knew the limits of their own knowledge. They were really concerned about this. And like, how much price inducement do I have to give someone for them to be willing to wait an extra 10 minutes or to walk a few blocks to meet the car rather than requiring the car to come all the way to them? So that was what they turned to conjoint analysis to do, to design this Uber pool service. And they had some hypotheses, but they didn't know the relative importance of the service attributes to customers. And so what they did was they followed a three-step approach. It was not unlike the Firefox segmentation example we went through, where first they did some ride-alongs and they watched people use Uber and they talked with them as they did. And then they did some in-home interviews. And that identified hypotheses, 6 service attributes that they wanted to test. They didn't want to put that many attributes into the conjoint, so they did something called a max diff survey. They asked people which attribute is the most important or the least important for subsets of attributes. And that process showed that the duration of the trip, the on-demand availability, and the time of arrival were the most important attributes. And that's what they put into the conjoint. So this was the attribute space that they tested, was how long do you have to wait for the car to show up? How far do you have to walk? Compared to a solo ride, how much longer is the estimated duration? And how much variance is there in that estimated duration? And then how big of a price discount do we have to give you in order to get you to prefer this? So overall, there were 900 different points in the attribute space that they tested. The choice task looked like this. There was always a no purchase option. So people could opt out if they didn't like these hypothetical choices that they saw. And they had 7 choice tasks per respondent. They recruited respondents by emailing a random 18,000 riders, invited them to complete a 5-minute survey, promised a $500 gift card to 5 randomly chosen participants. And that got them nearly 2,000 survey completions at just about $1.29 per survey. And then they used the data to estimate this hierarchical Bayesian logit model, which is a flavor of the individual level heterogeneity that I showed you earlier. And so they don't give us the y-axis, but they give us the relative attribute betas. And as you can see, the price level was relatively very, very important. The variance in the trip duration didn't seem to be nearly as important as the estimate of the trip duration. People were willing to walk to some degree, and the availability mattered to a moderate degree. And then they used that estimated model to decide how to design the service, which they implemented. The details are in the paper. They interpreted a falling cancellation rate after introduction as evidence of product launch success. This type, it's kind of like how companies usually don't publish their demand models. They don't want their competitors to know. This is maybe one of the weaknesses of this paper, is that the indicator of success could be a bit better. And so I think that illustrates how conjoint gets used, why it's useful. There are some really great aspects to it. Because everything is experimental, there's no worry about price endogeneity. We can test any product or service that we can think of. It's relatively quick and it can be confidential. It's not launched in the market. And there's a mature industry of specialists in running these studies. The two major downsides, in my opinion, are getting a representative sample can be really hard. And getting people to accurately predict their counterfactual behaviors. It's questionable in many settings, like if you're eating at the ballpark. So this idea is like 50 years old. It's been extended into every direction you can think of. Whatever criticism you might have of this framework, there exist multiple solutions to address that criticism. Doesn't mean that they all work perfectly, but this is a really large and popular area. To wrap up, what I hope you can take away from today is that understanding customer heterogeneity enables really profitable strategies that would be hard or maybe impossible to find otherwise. There are three main ways that we can incorporate heterogeneity into our demand model. It typically helps the model to fit better, but it may cause the model's predictions to suffer. So we have to balance our objective criteria. And one of the most popular ways this gets used is in stated preference data through conjoint analysis to decide what types of products to offer in the future. Thank you so much. I am looking forward to seeing you next week. We'll talk about pricing and how to use our demand models to optimize our prices.